mandatory slide. Mandatory slide for me is they have to give a brief rundown of star formation. So we know stars form from molecular clouds that collapse by gravitational force. And then we start with a protostar that is embedded in this dusty material of the cloud that is continued to fall in. The material will fall into a disk, and then from which the star will accrete, and then with time, the star stops accreting, the disk dissipates by photoevaporation, accretion, and other mechanisms, and then you end up with a star of the main sequence with hopefully an exoplanet system. And like I said, I focus mostly on T Tauri stars or young low mass stars, mostly between this period where they're still accreting and they're maybe not accreting at some point. And this is now the time we know planet formation starts. We know planets must form very early, maybe even earlier than these stages. So it's a very interesting age to kind of try to piece together how planet formation works. But of course, it's always more complex than what we maybe hope so in when we're trying to do science. The way we try to study this protoplanetary disk is you can study the gas, you can study the dust. We know closer to the star, they have higher temperatures than further out, so that will mainly constrain what kind of molecules and ices you will see. But depending on the size of the dust, it will move with the gas, or it can move completely independently. It can, if the bigger you are, you can settle and then move radially inwards faster than the gas itself. So that this can look very differently in depending which wavelength you look at it. And here it is, you have these beautiful plots of TW Hydra, one of the most famous disks, and different molecules, how it looks when different molecules, how it looks by continuum emission, how it looks when scattered light. So a way that we study these kind of complex processes within the disk is by looking at the elemental abundances to kind of probe the different regions of the disk and what's happening and put the whole story of the processes together. Sounds way more simple than what it is, but with this we hope to constrain dust evolution and planet formation models so we can have a more informed view of these processes, and then you can also use it to characterize, and hopefully in the future, to characterize atmospheric composition of any exoplanets, because we know any planet that forms will inherit the composition of the place it formed in the disk. So that's something that it's a very prospect, like promising prospect in this kind of area. And then we can also use it to understand the formation of the solar system, solid bodies that we have nowadays. And we do it separating rods versus ices, or refractories versus volatiles. So refractories are those elements that need high temperatures to sublimate or turn back to the gas. So think temperatures of like 1500 kelvins, things like magnesium, iron, calcium, where it will be essentially locked in the disk from the very beginning, versus ices, or volatiles, where you need lower temperatures, and then you will have this whole sublimation further out, and that's where you have the different snow lines and all these different kind of properties that we're now seeing with JWST, which is amazing. My little contribution to this area is studying the rocky material. We know that all planets have a rocky core. You need to form a rocky core to form a planet, the first instance. So we need to have concentration of dust so it can grow. And this how you pass from the micro size dust to the kilometers of planetesimals. It's a whole field of theory that it's always in development. But as a community, we always point out substructures. So we now know substructures doesn't mean they have a planet, but we know substructures are directly involved with planet formation processes. Whether it happened first or it happened after the planet form is a way that dust get accumulated, and by that it will promote dust to be concentrated and potentially form these planetesimals. So what I do is to try to prove if there is dust, what's the history of this rocky material from the accretion flows. So this is a more schematic, another version of the schematic view of the disk, but now concentrating in the innermost disk. So this is the dust disk, and within like 0.1 IU, you will have what is called the hot dust wall. That's where the disk reaches temperatures about 1500 Kelvin. So all dust is sublimated and returns to the gas, and you have the inner gas disk, and then the inner gas disk for T30 stars gets truncated by the magnetic field of the star, and the material only option is to follow the magnetospheric field lines into the star in what we call these accretion flows. And once it reaches the accretion flows, you will have an accretion shock, and we can see all these different parts in the optical kind of near infrared side of the spectra. In the near infrared, you will have the excess from the dust wall. And then the UV, you will have the accretion shock. But during the optical in wavelength range, you have all these broad emission lines that form the accretion flows that basically are telling you what's the surviving material reaching past the dust wall. What is the composition of the inner gas disk? And this, again, it can be very interesting in the sense of we can prove if there is some kind of weird, peculiar abundances of elements that can tell us a bit of what the history of the material further out in the disk is. This is essentially what my PhD is about. And I first started with calcium. And a lot of people ask me, why calcium? Why use calcium as a proxy for rocky material when most people think about iron and magnesium? Well, calcium is one of the most refractory elements. It's an important component of the conduit material in the solar system for like the calcium aluminum inclusions that you can find in meteorites that are actually used to mark time equals 0 in the evolution time of the solar system. So we know they are in pebbles from the very beginning and of the evolution of the system. And we know they're considerably sized pebbles, so they're going to be settled and moving differently than the gas. And also calcium has one of the strongest lines for metal elements in the optical range, which to anybody that does some kind of observation know that helps a lot when you're trying to get some estimate and you want high signature, right? So having a strong line always helps. And saying that, I started my PhD doing a project with chameleon-1 stars, where I did a systematic analysis of the calcium-2 lines. And we found something really interesting in some stars that looked like they were missing calcium. So I have here a plot of the line profiles with the flux relative to the continuum of H-alpha, calcium K line, and calcium, one of the infrared triplet lines. So in the top row, we have SC37, and in the bottom row, we have T28. These two stars are from the chameleon-1 cloud, so they have similar conditions. They're from the same parent cloud, so they should have roughly, within error bars, same composition initially. They have comparable spectral types and accretion rates within the uncertainties. We know that accretion rate correlates with the luminosity of H-alpha, which can prove the density and temperature of the accretion flow. So if we look at H-alpha for the two stars, we notice that have these broad, strong profiles that we expect for the high accretion rates that these stars have. But when we look at the calcium lines, we can notice straight away there is a really, really big difference between SC37 and T28, in the sense that T28 have really weak and narrow calcium-2 lines. So this was very puzzling because, again, you see that there is gas accreting, there is material accreting into the stars because you can see it in the H-alpha, but it doesn't seem that T28 had a lot of calcium in this gas that is accreting at the same time. So for it to not be calcium, again, if you think back of the schematic picture, so if we're measuring the material that is falling at the same time in the accretion flow, for it to be hydrogen, so gas, but not calcium, that means that there is no hydrogen or calcium in the inner gas disk. So that means that the calcium is, or the rocky material is not getting past the dust bubble, it's not returning to the inner gas disk. So we took this as it was actually a very interesting surprise. We didn't think we would find something like this. So we started thinking, well, this must be some kind of pressure bump that must happen, right? Because if you have, again, another different schematic picture of the disk, so you have the dust and you have the ices in the in the pebble settle down. As you pass the different snow lines, these volatiles will return to the gas, but the rocky material will always stay in the pebble. So the only way they don't appear in the inner gas disk is that they're getting trapped outside. So ideally, I would like to say it's a planet. I cannot say that further out, or at least this soon. And there is also the question of the radial drift, which I will address further on in the talk. But before I had to get too excited to this, we have to ask, well, how significant is this change in calcium? So significant is this calcium depletion that we're seeing? So for this, we model the lines using the magnetospheric accretion model that uses a standard Sobolev approximation or a large velocity gradient. And it takes the accretion rate, the temperature distribution of the flow, the geometry of the flow, of the accretion flow's inclination, and now the abundance to predict what the profiles of the star should look like. And we did this modeling for a large range of spectral types and accretion rates to try to kind of gauge the whole range of parameters our observations were. And again, we use the with T-Tauri star spectra, a T-Tauri star that is not accreting, so it's a proxy for the chromosphere, which is actually very important for this star, as a model for the chromospheric activity. We also have these observations with the same resolution, which was also important to include. And we ran a test study for T28. That is the star that I compared you before, but I have here a reminder how the profiles look like. Very strong H-alpha, very weak calcium. And we found that we could, first of all, it was a very nice result that we could reproduce all the fluxes of the line simultaneously and the equivalent width of H-alpha at the same time. But for that to happen, we needed to lower the abundance of the calcium abundance of the accretion flows. We couldn't find a combination of parameters with solar abundance, which is what it's expected for this type of stars, unless we lower it. And it was a significant change. We found that for this to actually reproduce the line fluxes, we needed 70% of the solar abundance, which is too low to be an initial condition outcome. It couldn't be like, oh, they just form different size of the cloud or like some magnetic field effect. It's too low to be explained by that. So it had to be some kind of process that happened to the dust in the disk that caused this. So that left us, this result left us with more questions than answers. We were very interested to follow up this result up. We were also interested to see if we see this behavior in other star-forming regions to see if there was a common behavior. And we started doing that by expanding the sample. Now, besides the Chameleon 1 data, we have Lupus and Orion 1b, which cover a very wide range in accretion rates and stellar parameters, but more importantly, age. And with this, we were trying to see if we can find kind of like an evolution with age to try to see if it's just a natural process of dust evolution or something else. And then we started calculating abundances for the whole sample. Now, we couldn't, I wish I could run an MCMC of detailed modeling for each target, but that was too expensive computationally. So we decided to do a more simplistic or coarse method, and we focus only in the H-alpha on the calcium K line, which we found while we're trying to do the test for T28, that was the ratio between the lines was something key when we were trying to reproduce both lines simultaneously. So this is a very busy plot, so I will walk through it. I have the ratio of the lines in the y-axis. I have the accretion rate in the x-axis. In color, I have the magnetospheric accretion model. So the more lighter color, the kind of washout colors are the models with a width star, and the brighter colors are the models with the width star. So again, taking account the chromospheric level of these stars have, which is significant, especially low accretors and earlier spectral types. And then we compare our models to the model grid that we also have for a very wide range of abundances. So that's the color. The purple is solar. The more red, the more depleted it is. And we calculated abundance by doing a 3D interpolation between the plot, the models, and the stars. So we noticed right away by just looking at the plot that there were some stars that we couldn't reproduce. There is no model that will reproduce these ratios unless you have lower abundance. Something I forgot to mention is that for each abundance, we are average out the line ratios for every single possible combination of parameters. So there is really no other combination of parameters that will give me this ratio unless besides that I add a depletion in calcium in the accretion flows. So for the results that we found is that we see the depletion in a lot of stars. It actually seems that it's very common, and we find 57% of the sample have abundance lower than 50% of solar, which is beyond the point you can say it's an initial processes or outcome. We see our peak around 20% solar, but we have some biases within that value that can prevent us to, the width stars essentially makes a floor into what we can measure. And most of the time it's around that 20% level. So we really cannot prove below that for low accretors stars. So that's where the peak is coming from. But it is looking towards lower abundances. And when you first look at the plot, you will think, you will expect to see, or you would like to say that there is a correlation with age, given that Orion 1b is the older sample and they're all depleted. We tried to run a statistical test to prove that, and they were not conclusive around that. They actually seem that likely they share the same underlying distribution. It might be that this dust process is not really related to age, but it also might be a consequence that the Orion 1b sample is significantly smaller than the lupus and chameleon, so that will affect the statistical results, how raw really sound they are. So that's something that we were working to expand this all sample in the future. We also then try to answer the question, is this really related to gaps and pressure bumps? And we did this collecting two different data. We were trying to just collect information from the literature for all these 70 stars. Well, do we know they have gaps or bumps? So we did this with the SED. We know that if you have a gap, then you have missing dust in the inner part, so you don't have that excess at low around 10 microns. You will have this dip in the SED, but also there is now a lot of stars that have high resolution imaging with ALMA, and then we can really prove when it's really, really the highest resolution if it's a gap or it's just some kind of substructure, like in case of SC128. And we found very interesting results. First of all transitional disks are depleted, which is significant. We kind of was a very good check when we were seeing the results, because if you have a transitional disk, you have a gap, you have a pressure bump, you have dust trapping, it makes sense. But we found a lot of full disk that also are depleted. Again, this could be hidden substructures that we cannot see. This is especially true for the chameleon one sample, since this doesn't have high resolution imaging. Most of the stars only have resolve gaps above 50 IU, which is huge. So there is a big uncertainty mark there. But there could be also part of that transport mechanism or radial drift that I mentioned before. So it's an open question of like, what is this portion of full disk that are highly depleted mean? Talking about radial drift is, again, I mentioned very early in my talk, that if the dust is bigger, it grows a bit, then it decouples from the gas and it moves radially inwards faster. That will mean that means different things for different elements. So volatiles, as they cross the different snow lines, it cannot replenish the material in the disk, but that doesn't seem to happen for refractory material. You will have an initial enrichment process at the very 0 to 2 million years, just given by the fact that the pebbles are moving faster, but then you have a natural depletion because you accreted the rocky material earlier, and then you have nothing else in the disk, and you cannot replenish that because it will be just in the pebble, in the rock that you accreted in the first million years. So that's an interesting thing to have in mind. However, it all depends on viscosity. In theoretical models, if you have high viscosities, then you have a slower radial drift, and this is not significant. So we found that there is we need more models essentially to disentangle the effects of radial drift of planet formation, because we know at some point the effects are like both things are happening. You will have radial drift and you have planet formation. And it will be really nice to have some kind of theoretical model that will predict what these two processes will make on the pebble abundance over the years. We also try to correlate with these stellar and disk parameters. We very quickly find that there is not much correlation. There is no correlation with stellar mass. There is no correlation with disk mass or the dust mass of the disk. And there is no correlation with the radius. But we did find a correlation with the accretion rate, which is the incredibly puzzling result that we still cannot explain to this day, because accretion rate correlates with mass of the star, but we don't find a correlation with mass at all. So we think this might be hitting to a dichotomy between the innermost disk and the outer regions, in the sense that the accretion rate is measuring the amount of material in the inner gas disk that is falling in, but the abundance itself is correlated to something that's happening further out. So just a thought to still have put out there, but still something that we don't really understand. So just as a recap, as I continue, we found calcium depletion of the Tauri stars, that we're using calcium as a proxy for this rocky material. All these with gaps have depletion, but the opposite is not true. Calcium abundance suggests that most of the inner gas disks actually are depleted in rocky material, which can have a lot of implications and a lot of discussion points. So I think it's very interesting that we're seeing trapping of dust by just looking at the spectra of the star. And this could also means that there is accumulation of dust happening, so there is potential for planet formation to be starting or to be actively happening. Again, I cannot say there is a planet, but I can say the conditions are happening for planetesimal formation at least. And we find an anti-correlation within the calcium abundance and accretion rate that we don't really understand yet. But this just leads to more things, like can we add more regions to kind of see the younger side, where you have this enrichment by radial drift, on the older populations to see if we can see this evolution trend that we kind of see with Orion 1b, but we cannot robustly say. What will happen with magnesium and iron? Can we say something about them? And what can the SED detailed modeling tell us about the dust composition further out? And compare this with the dust evolution models. So this is kind of in the direction where I'm going. Started with magnesium. As always, you think you start with a project, it's like, this is a cool idea. And then everything turns out more complicated than than you think so. We started with the DAO HSD sample, which is part of the Ulysses HSD archival data. Ulysses is a project team that has observed and accumulated about 500 hours of HSD for T-Tauri stars. It's a beautiful collection of data. It has around 20 Taurus stars with high resolution spectra. So with this, we're kind of checking also that younger sample that we're interested to. But yeah, we clearly find out that these have huge wins in essentially 90% of the sample. There is high blue shifted absorption, optically thick. Most of them are saturated. So it's becoming really tricky to try to say something about it, but the model implementation is underway. As it seems, since they're very strong, resonant, optically thick, it's becoming really hard to try to say something with the abundance. Where in this case, I'll show you here BP tau. And then the black line is solar abundance versus 10% abundance in the red line. So they're very, very similar in the sense that the difference between them is not, you need very detailed modeling to be able to pinpoint, and even then, the error bars are looking huge. But it's underway. We think it might be promising for the low accretion stars where you don't have this optically, they're not saturated because you have lower density, because you have low accretion rates, which is something that's actually interesting to explore, because that's where we're having trouble with the calcium lines, because you have the chromosphere. So it's just an interesting new prof, and try to explore what we can say about it. And then I'm also doing a detailed multi-wavelength view of BB tau, so the same star that I was showing you before. This is how the spectra look like in the optical with in the Magellan telescope. So we have, again, very big, broad H alphas. So there is a lot of accretion going on, but the calcium lines look very, very weak. I started trying to do detailed modeling of the calcium profile for the calcium 2K line, and we find abundances about 10% of the solar. This is the 0.1 of the solar abundances. By the line ratio method, we get abundances about 6% solar. So we're actually kind of very happy that these modelings seem to give consistent results. It's still not perfect. This work in progress, that it's happening. So we're trying the goal is to model the optical lines with H alpha and the calcium, and try to constrain the geometry so we can further constrain the models that will go into the magnesium to see what magnesium can tell us. Because in principle, there shouldn't be a difference between magnesium and calcium, but that's the ideal place. And something that is really interesting also about this target in particular is that if you look at the ALMA data, you don't see a structure at all in the disk. But again, you see the very, very depleted profiles in calcium. And I've been working with an undergrad here, Justin Spark, in University of Michigan, doing the detailed modeling of the ACD. Again, work in progress, but we got a pretty decent fit so far. We need a gap actually within 10 AU to be able to reproduce the SED in detail, which is hinted at from the ALMA data analysis. They can see it in they call it PSF, but it's not obvious in the image. It was pretty nice to see that we can actually see it in the SED. More interestingly, we need different composition of dust for the outer and inner part, depending on the gap, which is, I think it's very, very interesting work. We need a more crystalline processes dust and the further out this to reproduce the 20 micron dust, but the 10 micron dust is more amorphous and more pristine. So it's something very interesting and kind of putting, the goal is to try to put this whole view of the multi-wavelength abundances of the rocky material to kind of pinpoint to the different processes that might be happening inside in the inner parts of the disk, which is also the location where most of the planets that we know so far are, although that's completely biased by detection methods, but again, very important population to try to explain. And yeah, in my summary, we found calcium depletion in these auditory stars and multiple star-forming regions. We find that the calcium depletion seems to be very common, and if we treat calcium as a proxy for refractory or rocky material, that means that rocky material is getting trapped further out in the disk, and we can see it with the optical spectra of the star, which I think is a very powerful tool. All this would have depletion, but the opposite is not true, but there might be some biases in what we can observe for these substructures. But I think it's also very interesting to try to see if we can prove there are different radial drift prescriptions or with viscosity descriptions that we see. So that's further work in process comparing with dust evolution models. And yeah, the next step is hopefully more refractory elements, more star-forming regions, and start to do a full detailed multi-wavelength view, including the SED modeling. And yeah, that's all. I appreciate any attention you gave me. And yeah, thank you again for inviting me and open to answer questions.
Can you go back to your summary slide? Thank you.
Let me start the first question. So my question is, when you're fitting the SED, did you see any degeneracy issue?
Can you repeat that, please?
When you're fitting the SED with
Yes.
different dust, then would you say some degeneracy issue?
If I understood correctly, your question, you're asking for the degeneracy in the fitting?
Degeneracy.
I'm sorry, my audio is not really, really great, so I'm hearing by pieces. Yes, degeneracy in the fitting. Yes, we find some degeneracy always with the composition, but we are very robustly can say that we cannot fit the 10 and 20 micron feature unless we have a gap. The gap is like there is no there is no, at least in our models, where we're using the DIAP models from the Alessio 2008 modeling of this of disk. With those models, there is no way that we can have those two different compositions within the full disk, because the 20 micron is very, very crystalline and the 10 micron is very amorphous. So you need to have this separation of dust. And the way we handle the prescription is with the with it being a gap, so we can also reproduce the intensity that we see. But yeah, it's a work in progress with the undergrad to try to kind of narrow down the error bars and to break the degeneracy to a certain point. About the composition itself of like how much is Fosterite and Estatite versus olivine and pyroxene. But we're very, very certain that you need a gap in the inner 10IU.
This is Olivier. I have a question. So I'm curious about. So you've been doing spectroscopy. I'm curious about spatial resolution. So I'm more on the instrument building side, and one thing I'm curious about is at what, if you could do spatially resolved spectroscopy, whether it's slit spectroscopy, and you had the potential to, you're showing velocity profiles for line. At what scale do you expect this velocity to be at the spatial scale? What if you could actually spatially resolve the line, so you could get the line at different location in the image?
That will be very interesting, actually. For now, I've been working with the Chameleon, Lupus, and Orion 1B sample is a shooter. So it's about 10,000. The microspectra is about its higher resolution. There is the idea that if you can resolve with like high resolution spectra, you could also. This model is very simplistic in the sense that you only have one flow, but we know that the flow might have, you only don't have only one flow, you have multiple flows, and the star is rotated. So if you have a very high resolution and you actually follow the star, you could also see the change in velocity as the column highs and comes up. That's
so what is the size? What is the physical size of the emission region? It's sort of a 10th of an AU, or?
No, it's all inside 0.1 AU. The accretion flows are typically between 3 and 5 stellar radii.
Okay.
Yeah. But you can,
Okay.
there has been some spectra that has proved that you can actually see it, the hiding and the coming out just for the rotation when you have a main accretion column and it hides, and you see when you follow the star with the velocity. But that, yeah, it was around mic resolution 30,000 for the
velocity. Okay, so in terms of spatial resolution, basically for the nearest targets, which probably the targets in Taurus, with ELTs, GMT, ELT, TMT, you could actually start getting spatially resolved those flows a few milliarcs ago. So that's interesting.
Yeah, it's one of the things that I have like, oh, this will be interesting to follow up once I saw that you can actually see it. But of course, that means applying for time, and it's always more complicated than that. It's like cool idea, and then you get rejected. But yeah, I know it's people have done it, and there is also, if you want to really especially see the dust, I know there is interferometry in the optical you can do with Chara and VLTI. And if I'm not remembering wrong, there is also a paper that shows that you can have like bluff of material moving inside that inner AU, which might be related, might not, not in that. I haven't read that much. But it's yeah, I think it's very interesting to see like what the dust is doing within 10IU or inside 10IU, because that's, first of all, when we see all these planets that we can detect so far, and that we don't have in our solar system. And it's a very active zone as its own, because it's high temperature. So chemistry is doing a lot of things, dust is doing a lot of things at the same time. So And you can have the dead zones too, because there is the region where potassium can actually be sublimated and ionization can happen, but you have the dead zone too. So you have dust trapping, which also is one of other theories to explain this depletion of calcium, that you can have dust trapping around the dust wall.
Okay, thank you. Yeah, very nice.
Yeah, thank you.
I have a question.
Yeah.
So when you mentioned that you can't see the gap in this system from the ALMA imaging, is that a sensitivity problem or is it a resolution problem?
Yeah, I'm not fully into ALMA data. For what I understand is sensitivity and resolution. I think if you I think for this particular target, you don't have the highest resolution observation. This paper, what Yamaguchi did was take all the archival data and kind of reprocess it and with another cleaning method of the data. And that's when they can find actually the hint of the inner, but it's also there is also the fact that these are kind of far away, and if the structure is really smart and really in the inner AU, you might not see it with ALMA because the ALMA cannot give you that much. You're asking too much of the instrument at that point. So I think it's interesting that we can kind of probe and see this smaller substructure closer to a star with spectra. But yeah, I think it will be amazing if we can, ALMA at some point can give you all the details. But I think when you're inside the 10IU, you're asking too much of it.
Yeah, I guess I was wondering, like, maybe, I don't know if this is something that NGVLA may possibly be able to do. I don't really know what kind of resolution NGVLA is expected to get, but maybe.
Yeah, that's actually, I haven't thought of that, but that's something to look at it to see what they can do in terms of resolution to reach those 10IU. Yeah, thank you.
I guess, okay, so I have like kind of a very speculative question, but how would you expect these accretion flows to be affected if you had like a stellar binary? So do you expect like, some disruption of the flows, or does that create some environment that is not really well suited for the kinds of accretion signatures you're looking for?
So far as I understand with binaries, I don't have a lot of understanding with close-in binaries, but a lot of these, well, not a lot, but some of these stars in the sample have binaries. And they agreed, and they all can have their own disk. What will happen, as far as I recall correctly, is that sometimes the disk can be smaller or have less mass, just because they're just with the binary and competing with the binary. So you might not have like high mass planets in that sense, because you don't have the mass available to it. I haven't in all honesty looked for a trend with binarity. It would be kind of fun to explore, but I also haven't seen something obvious that will pinpoint to like something that it's happening with the binaries. Because yeah, in principle, each one has their own disk and they're doing their own stuff. It's just that probably some kind of the disks are not that massive.
Thanks.
Yeah, so just like there may be some other scenario that the photostar also capture the nearby gas. If there's H cloud nearby, then sometimes the photostar will capture the gas from those clouds. Yeah, and it may also impact the CA ratio.
That's a good question. I mean, we haven't found any sign for enrichment, which we think it might be just an age thing. The three main samples that we have looked at, they have been older than, around 2 to 3 million years, which they're all according to, if we follow the models from, where are they? If we follow these models, after 2-3 million years, they should have been depleted. So if they capture something and they get enriched, we couldn't really see a trend for enrichment. So in that sense, we're a little bit blind, but we haven't found an obvious trend to it. I also wouldn't be able to right now tell you what will be a good probe for it either. At least not in those ages. That's also why we're starting to move towards Taurus too, to try to see, Taurus is younger, so try to see if we can find some kind of different behavior with Taurus that we don't see with these other three main star-forming regions, and we can see some kind of enrichment, something else that we can talk about. Did I answer your question? Sorry.
Yeah. Question? Let's Marbely again.
Thank you so much for inviting me.
Don't forget about the